Good morning, good afternoon, and good evening, everyone, wherever you might be. So today we're going to be doing something a little bit different. We're actually going to do a bit of fun applications of this math stuff. Because I know you guys don't just want to be seeing like formulas and stuff. So I'm actually also going to incorporate some fun stuff here. So I bet you guys have heard of Angry Birds, right? I mean, it's the game where you you have your set of birds and you have to hit the pig basically. So you're gonna like load up the bird in a catapult, no, not catapult, like a slingshot, and then you're gonna release it, and then your goal is to be able to hit all of the pigs. So yeah, that's pretty sure it's a well-known game. So yeah, um here we're actually gonna apply some math here. What we're gonna be doing um, is we're going to hit the pig. Yeah, that's what we're gonna be doing. We're gonna hit the pig um, based on 2 points. So how does this work? Well, you guys know what a coordinate system is. Sorry, bird. So this is a coordinate system, and the idea is my bird here, or my angry bird, uh, it's at this point 0, 0. Let's say my bird's at the origin, and let's say my pig is let's extend it here. My pig is here, and so this is the point. Um, well, this is some point, right? Some point from the to the Cartesian plane here, the xy plane. And so given those 2 points, how can we determine um, if this bird's gonna hit the pig? So so if we're given 2 points, how are we going to be able to um, hit the pig? So maybe we might want to use like some angles here, some curves, because when you use the slingshot, right? Like we pull back the bird, we're pulling back the bird, and then when we release that slingshot, it's gonna go up, and then eventually it's gonna hit somewhere, not necessarily the pig, although it could hit the pig if you're really good at aiming. The bird could land like here, or it could land, I don't know, here at some other points. Or it could land in a structure, I don't know. Or, lucky enough, it could even land on the pig. So, yeah, let's actually try and do that. So, we're gonna make it general here at first, and we're gonna plug in some points. So, the bird is, let's say, at the origin. Let's keep it simple. The pig is at some point. Let's just say this is the pig's x and y. So, let's do x pig and then y pig. Yeah, so this has the point x pig, y pig. Okay. So when we're pulling the bird going kind of downwards, we're making an angle, right? So we're making some sort of angle. And in the game, right? When we pull back the bird using that slingshot, it kind of gives us like a direction of where it's gonna go. You know that? And then if we pull it even further, then the path is going to kind of be a bit straighter, right? So that happens in the game. So how are we going to do this? Well, we want to choose an angle or maybe some initial velocity, but we can't really look at the velocity, right? Like, I mean, we don't see it in game. But we can choose an angle or the velocity, I don't know, so that the bird hits that pig. So for this problem of hitting the pig, we're going to use this idea of projectile motion equations. And we're also going to use a little bit of calculus to help us with reasoning a bunch of stuff. So step one, well, we need our projectile motion equations. What do I mean when I say projectile motion equations? Well, these are equations that will help us determine the position of the bird given some time. So let's say the bird is here. Let's say this is at time like 2 seconds. At 2 seconds, the bird is in this point. So it's now here at some xy, right? X and then some y. And so we're going to make equations out of that so that we can determine the position of the bird. Ideally, it should be at x pig and y pig. So if the bird is in that position, then that means we hit the pig, right? If the bird reaches at this position, x pig, y pig, then it means we hit the pig. So yeah, for projectile motion equations, we need some sort of x function. So given some time t, we're going to determine what's our x position. Are we here in x? Are we here in x? Are we there? And we also need some y position. So for y, are we here? Are we here? Are we here? Are we here? And we're going to combine those, right? So how do we get that? Well, here we can use a little bit of, well, we actually kind of learned this in physics. Um, but the idea is we want to break down the initial velocity into components. So let's imagine we have an initial velocity. Obviously, it's zero, right? Because we haven't moved it. We haven't moved the bird yet. So let's actually use a bit of calculus here just to break things down. We have our velocity vector. So we did talk about vectors in previous discussions. So let's say we have this velocity vector v naught, which denotes as the initial velocity. And so how does this look like? Well, right, if we pull the bird down, it's going to make a velocity vector kind of like that. It's going to go up, sort of, like upper right-ish. I'm actually going to leave that. Yeah, let's leave it like that. So we have that velocity vector initially. And what does that do? Well, it actually makes an angle. It makes this angle here towards the x-axis. And let's just say that angle is theta, right? Now, how do we find the velocity? Here, we actually have two velocities that we want to consider. We have two velocities. How fast is the bird going horizontally, right? How fast is it going horizontally? So that's the x part. So this is v sub x. Like how fast is the bird going left or right? And then how fast is the bird going vertically? So this is vy. Is it going up? Is it going down? Pretty much. Now if we combine that, we get, yeah. So there's this idea. Okay. So for our initial velocity horizontal, let's just call it horizontal and vertical velocity. I don't know if there's a term for it in physics, but I'll just call it that. So for our horizontal velocity, we can say that Vx, let's say the initial is this. So Vx initial, so the initial velocity at x is going to be the initial velocity times cosine theta. Now, how in the world did cosine theta get in there? How did we come up with this equation? Well, this is actually trig. So here we can see from this diagram here, that's kind of a right triangle. If we go down, that's a right triangle, right? So that's a right triangle. And here we're going what? Wait, here's our angle theta, right? From here. Our vector is here, our initial vector v naught. Now, what's cosine of theta? Cosine of theta is this side divided by this side, right? So this is our Vx naught. So this is our initial velocity that's going right. So cosine theta, if we remember our trig, it's the adjacent side, so this side, over the hypotenuse, which is the longest side of a right triangle. So the adjacent side, which is Vx naught over the hypotenuse. And then so that's where we got this stuff. And then we can actually just multiply V naught to both sides. So we actually get Vx naught, V naught cosine theta. So that's where we got that. And similarly, so that's the first case for our horizontal velocity. For our vertical, so the one that's going up, in this case here we use sine. So we have sine, cosine, tangent, which is the basic trig functions. I call them functions. So now we're trying to get Vy initial. This is just V naught sine theta. How do we get that? Well, again, we did trigonometry. So this is Vy naught, right? Because it's going up. That's our initial speed in terms of vertical. And so we just use sine, just write it down here. Sine theta is the opposite divided by hypotenuse. So it's the opposite divided by hypotenuse. And now we can just divide, or we can multiply V naught to both sides. So we get this equation. So that's how we were able to get both of them. So using a little bit of trig here. Okay, so now we have our initial Vx and Vy. Let me quickly put this here. Now, next is, so in physics, we not only have the velocity in terms of going up and down, but when we're on planet Earth, so this is physics, which I suck at because I flunked my physics class. So in physics, we have this thing called acceleration due to gravity, right? Because since we're on Earth, we have gravity. So we have this thing. I'm afraid I don't know what this is in depth, but apparently it's used a lot. And the idea of gravity is when you're on planet Earth, you're always, I guess, you're always staying on the ground, sort of. And it's because you're being like, okay, I don't wanna explain too much, but you're not like floating anywhere. You're just on Earth because you have gravity. And so here's what I can explain, which is if we apply this concept again of vectors, so let's say acceleration. So, okay, let's look at Earth again. Trust me, this is Earth. We have me, I'm kidding. We have a person, and it's that person is being um it's being pushed. I'm gonna say pushed, okay, or pulled down, pushed or pulled down to Earth. That's why that person doesn't go out. And here, if we notice these like arrows, we can actually denote that as vectors. So let's just do one of them. Let's say this one. We can actually represent this as a vector. Let's say A, because A for acceleration due to gravity. And this acceleration here just has components 0, negative, G. G is gravity. Why is it negative? Because it's going down, right? Hmm. Why is it 2? Because we're looking at this from a 2D perspective. And because the game is 2D. So, I don't know, unless I haven't played Angry Birds for a while, but I know the game is in 2D, right? Last time I played was like what? When I was like a kid, like 2013 or something. I don't know. But yeah, so that's our vector. Our x component is nothing. Our y component is it's always kind of going down. That's why it's negative because we're being sort of pushed down. And so we want to take that into account when we're finding the motion of the bird, right? So that's that. Um, so here we don't have a horizontal accelerate. Um, for our horizontal motion, so now we have this. For our horizontal motion, so moving left and right of the bird, well, we have no acceleration here. I don't think we do, unless there's something in physics that says we do. Our velocity is constant in the game, and so that means our position is just x of t is this initial velocity times some time, right? And then from earlier, we said this Vx naught is equal to V naught cosine theta. So it's just V naught cosine theta t. And for our vertical motion, here, for our vertical motion, here we have acceleration because this is where we're being sort of pushed down to earth, to the ground, when we're trying to go up, right? So we have, we actually have an acceleration here, unlike the horizontal motion. So our acceleration here is just sum a sub y. I'm just saying y because it's the y-axis. I'm trying to relate it to math. And this is equal to negative g because that's our gravity going down. And so our velocity over time, so vy of t, our velocity is actually changing, right? Because if we, let's say if we throw a ball, not even the bird, or actually we can use the bird. If we like slingshot the bird up, then at first it's going to be super fast, right? And then if it reaches, I don't know, somewhere at the top, it's gonna slow down. And then if it goes down, then it's probably gonna go fast because of the gravity. So our velocity here for vertical, it actually varies based on some time that we're given. So here we can just say our initial velocity, so Vy naught, which we computed earlier. Now we're subtracting minus gt because we're taking into account the gravity. And then Vy naught, which we got earlier, Vy naught is V naught sine theta. And so we're going to use that. So this is V naught sine theta minus gt. Okay, and so our vertical motion is just y of t, vy naught. I say vy naught. Why not? Actually, no. Screw it. Let's just do. Actually, yeah, sure. Let's just do that. So vy naught um minus one half gt squared. Now, where in the world did they get minus one half gt squared? Um, Actually, I haven't been able to figure that one out myself. Um, but based on some physics concept, that's how they did it, which is totally weird. I don't know, but that's how they did it. And so I'm just gonna trust that this works. Um, I don't know, actually, wait, I think I can figure it out. T squared. Wait a minute. Wait. No, I can't figure it out. Never mind. Yeah. Um, By not. I was thinking maybe we get like the velocity of y and we're multiplying it to some time. And so this is just v naught sine theta minus gt, which we're multiplying by t. And so we have v naught sine theta t minus gt squared. But then, where did the minus one half come from? Yeah, probably like, I don't know where did the minus one half come from. We're gonna actually look that up right now. Oh, um, oh, it's calculus. Yeah, it's calculus. So again, I was kind of confused where the minus one half came from, but it's actually just calculus. Yeah. So if we're given some velocity and we want to get the position, right? Then we do some integral calculus to do that. Yeah, I just realized that. Huh. Yeah. So given some Vy of t, right? Let's actually just do this. If we want to get the position, right? Then we want to get the derivative of this thing. So we want to get the derivative of that to get the position. So right from velocity, no, I'm kidding, not derivative, antiderivative. So this is some Calc 2 stuff. We want to get the derivative, the antiderivative of this thing here. Yeah. So dt. So this is just going to be v naught sine theta minus gt dt. Yeah. And then, yeah, we just integrate that whole thing. And so we'll basically get v naught sine theta times t, there we go, minus one half gt squared plus some constant, which we don't care. So yeah, that's how we were able to get that. So from, because here's the idea. I'm not gonna talk about it in depth. I might do in a future video, but in Calc 1, okay, I'm just gonna explain for a bit. In Calc 1, let's say we're driving a car, right? We're driving a car and we have this plane yx, and the car is going some distance. So let's say this is actually not yx. Let's say this is time. This is distance. So let's say, I don't know, the car is going at some distance. And then if we go constant here, what does that mean? If this is the car, then that means at time zero, our car, the distance traveled by the car is zero. After some time here, time, let's say after 5 seconds, our car traveled this amount of distance. I don't know what that is. So yeah. But what if, let's say, we want to get the speed? Well, if we want to get the speed, well, let's do that line again. So after some time, we get the distance of the car traveled. So how do we get the speed? Well, in high school, to get the speed, we have this thing called distance. I might be wrong. Distance divided by time is speed, right? And so here we just divide the distance by the time to get the speed. So that's that. But now, what if my car does this? You know, it's not always constant speed, right? Um, how does that work? Well, that's when we use calculus. So given this function, we take the derivative. Let's say this is f of x. We take the derivative of that. We get f prime x, or another notation would be dy dx. And then we'll get the speed at some point. Let's say we're here. We know what the speed of the car is. We just plug in, let's say this is sometime 5. This is 5. Then we just find f prime 5. Or we're here. Let's say this is 8. Then we just find f prime 8. And then we'll get the speed in, let's say, meters per second. So that's Calc 1 stuff. Now Calc 2 is the reverse. So Calc 2, what do I mean by reverse? This is time. And now we're given the speed. And now we have some curve here. Let's say car distance again, or not like that. Speed is constant like this, ideally. That's the easier one if everything's constant. Now, what is this? Well, um, based on some time and some speed, we can get the distance. We just multiply speed and time to get distance, right? So how does that work? Well, here, let's say my car is at the speed. At this time, it's pretty much the same speed. And now my distance is, if you just multiply, then we get the distance. But then what if my speed is, I don't know, because of traffic, or I stopped, or I parked, or I accelerated. So here my car's like going super fast, and then like, oh, it's kind of, I don't know, it bumped someone. Okay, I'm kidding. And then yeah. So basically, the speed is not consistent. It's not constant. So how do we get the distance of the car? Well, that's when we actually get the area underneath. So let's say he's the guy who's driving is right here. What do I mean? His speed's right here. So we just want to find the area under this curve, and the area under this curve is basically the distance. So I know it's magic. I didn't, Newton invented that stuff. So yeah. So let's say this is again some function f, this curve. So to get that distance, then we just take the integral. So that's Calc 2. And so similarly, from our vertical motion here, well, we just we're given the speed or velocity, and so we take the integral of that to find the distance or the vertical motion, the vertical position, how much the bird has traveled vertically. So we use integrals to do that, or some Calc 2 stuff. Right now I'm learning Calc 3 and I'm making videos on that. So yeah, I'm gonna stop here for now. I'm gonna continue this later because again, I don't want the videos to be too long. So yeah, hope you guys enjoyed and stay tuned for the next couple of videos on this fun hit the pig Angry Bird stuff. See you guys.